RF Man here. Today I want to talk about L matching networks. In the past I've discussed different methods for impedance matching. Most of them have been focused on using some type of transformer, either a conventional transformer or a transmission line transformer, what we typically call a TLT. But today I want to talk about an L network. So what are L networks? Okay, before we actually show you the schematic, we'll go ahead and talk about why we need impedance matching. Okay, so I think many of us understand the maximum power transfer theory. Basically, that states that the maximum power is transferred from the source impedance to the load impedance when both the source impedance and load impedance are equal. And you can prove that with Ohm's law very easily. Also, when you satisfy this requirement of the source resistance and load resistance being equal, there's also either no reflected power or a minimal amount of reflected power. So that's basically why impedance matching is so important. Particularly for amplifiers. It could be audio amplifier, it could be an RF amplifier, but we need to ensure that the source impedance and the load impedance are equal. So for example, if we take an audio system, right, our load impedance or load resistance, I'm going to use both of those terms interchangeably. The load resistance typically is an 8 ohm speaker. So the audio amplifier, the output stage, has to be designed to drive an 8 ohm load so that there's no reflected power and that we transfer the maximum amount of power to the speaker. Okay, same is true with an RF amplifier, okay, but in this case, we want to transfer all that power to our antenna. So that's the main reason for impedance matching. So L networks, what are the various uses for L networks? Well, we already said to match impedance, but what does that do for us for an RF system? Well, it minimizes the signal reflection, right? The amount of signal being reflected back into the amplifier. It reduces the standing wave ratio or voltage standing wave ratio, and as we said, maximizes the power transfer, which ultimately improves the circuit efficiency. So these are the main uses of an L network, to try to match one impedance to another or one load to another load. So this is what an L matching network looks like. And there's a lot of variations. As you can see, I've got these two highlighted here. But this particular one uses a series capacitance and a parallel, or what I'll call a shunt inductor. Okay, so this is a very, very common type. Okay, and you can see the capacitor could be either on the source side or the load side. So we'll talk a little bit about why that is. Okay, another common type is when we have a series inductor and a shunt capacitor. Okay, and the same thing, the shunt capacitor could either be on the source side here or on the load side. Okay, and then there's other variations, as you can see, using combination of different capacitor values and in different inductor values. But the main idea here is that the L network is L-shaped and only really consists of two components. Okay, and typically when we design a circuit, we're talking about using lump components like these. So you might have a variable inductor that you can adjust or tune, or perhaps a fixed inductor. The same with the capacitors. You might have a trimmer capacitor like this one that I'm holding, ceramic trimmer, or possibly a silver mica capacitor like you see there. Okay, for the demonstration of using the L network, I've decided to use basically an oversized version of these components. here's my tunable inductor, and here's my tunable capacitor. And I use these oversized components so it's easier to see in the video. We're going to actually take a look at the effects of using L and C in different combinations to see how we would actually do a impedance transformation from one impedance to the other. So this is basically the circuits that are used. We're going to be focused, as I said, on these two. And how does it work? Well, without getting into the mathematics, and these formulas could be a little bit tedious to use, there's a lot of online calculators that make it relatively simple, and I'm going to go ahead and demonstrate one of those during the video. But real simple. Okay, we have our source resistance here, okay, which is 50 ohms, and we have our load resistance here, which is 25 ohms, okay, and that's the real part, okay. When we talk about impedances, we typically talk about a complex impedance. So we have a real part, which is the resistance, and an imaginary part, and we use the letter J to signify the imaginary part. We have either plus J or minus J. So plus J would be inductive reactance, minus J is capacitive reactance. And these circuits are used to transform the source impedance to a load impedance. Okay, so in this example, we're going to go from 50 ohms to 25 ohms. And I'm going to actually demonstrate that using these oversized components that you saw a minute ago. All right, so what are we actually doing here? Well, we want to match the real part, okay? So we want to transform the 25 ohms to 50 ohms so we have a direct match, okay? So we want to match RL and RS, okay? But then we also need to cancel out the remaining reactances, okay? Which is the imaginary part, okay? And we use what's called a congruent pair. Don't let that mathematical term scare you. Basically, it's just a pair of opposite numbers. So I think we realize that capacitive reactance and inductive reactance cancel each other out, right? So when we use this congruent pair, they actually have a canceling effect. And we're going to see that when we demonstrate the L network and take a look at it on the Smith chart. So that's the purpose here, to transform RL so it's equal to RS, okay? And then we have our maximum power transfer between the source resistance and the load resistance. So here are the two L networks that I'd like to talk about. And I already mentioned that in one case we have the capacitor, the shunt capacitor on the source side, and in another case we have the shunt capacitor on the load side, okay? So we use this configuration when the load resistance is less than the source resistance, and we use this configuration when the load resistance is greater than the source resistance. Okay, so in our case, okay, we're going to be looking at this example. We're going to have 50 ohms from our NanoVNA. Okay, that's our source. And we're going to show a match to a 50 ohm load. And then later on in the video, we're going to show how we can match to a 25 ohm load using this L network. So that's basically an overview of what we'll be doing. So first, I'm going to start by looking at the impedance of just a 50 ohm load. So let me go ahead and set that up, and I'll be back in a minute. All right, so now I have the NanoVNA set up with my software, and I'm sweeping this from 1 megahertz to 50 megahertz, and I've got my 50 ohm dummy load connected, as you can see here. So basically we expect to be at the center of the Smith chart, which is also 50 ohms. Now let me just explain the Smith chart again briefly for those of you who might not be familiar with it. But the center of the chart is our 50 ohms, right? All our RF systems are normalized at 50 ohm impedance. These circles are the constant resistance circles that you see here. So this is the constant resistance circle for 50 ohms. This line is where we have zero reactance. In the upper half of the chart, we have inductive reactance. In the lower half of the chart, we have capacitive reactance. So plus J, minus J. So with a 50 ohm purely resistive load, which is the real part, we'd be at the center of the chart, which is what you see there. Now I'm going to switch this over, and first we're going to add some inductive reactance, and then we're going to add some capacitive reactance, and we're going to see exactly what the results are. So bear with me here as I switch this over. And this is refreshing about every 2 or 3 seconds. So now what we have here is my inductor, and I got my 50 ohm load, as you can see there, same load, and I can vary the inductance by changing the position of this jumper and just bypassing some of the windings. And let's go ahead and do that and see what the effect is on the Smith chart. So I'm going to just gradually lower the inductance. We have to give the software just a few seconds to update. There you can see it's starting to move toward the center of the chart, and it's rotating in the counterclockwise direction. Now we'll reduce it a little further. You can see more rotation, getting closer to the center. And one more time, we can see it rotate further and get even closer. Now I don't have the full range that I need here to get right to the center of the chart, but you get the idea. Okay, as we decrease the inductance, okay, we move toward the center of the chart and we rotate in the counterclockwise position. So that's the key point here. It's counterclockwise. And again, we're sweeping from 1 megahertz to 50 megahertz. The pointer is right now on 25 megahertz. Later on, I'm going to show an impedance matching circuit at around 10 megahertz, which is right there. It's at 10.3 is the closest I can get due to the limited resolution of the software. Okay, so now I'm going to keep that on 10 megahertz, and we'll go ahead and switch this over and take a look at what happens when we add capacitive reactance. Okay, so right now we've got the same kind of setup. Here's my 50 ohm load, and we just have a series capacitor in line with the real part, the 50 ohms, and I can adjust the capacitance accordingly. Okay, so let's go back and look at the Smith chart. Let's see what happens here. Okay, now as I decrease the capacitive reactance, okay, I move toward the center. Okay, so I'm decreasing the reactance, and I'm moving closer and closer to the center point on the chart. And you'll notice that the rotation now is clockwise. And that's important. With the inductance, the rotation was counterclockwise, and here the rotation is clockwise. And this is how we can basically use a capacitor and inductor to counteract one another. Okay, so now I'm going to set this up, and I'm going to put the capacitor and inductor in series and show the results of that as well. All right, so now I want to show the interaction between capacitive reactance and inductive reactance. So what I have here is my 50 ohm load, and I have my variable capacitor in series with my variable inductor. And the purpose of this is just to show the interaction of the two on the Smith chart. So let's go back to the Smith chart. And you can see right now that the circuit is more inductive. Okay, my marker, which is at 10.3 megahertz, is on the upper side of the chart, so it's inductive. So we'd have to add capacitive reactance to move the marker closer to the center of the chart. So I'm just going to slowly rotate the variable capacitor. I'm going to increase the capacitive reactance, and you see that I'm moving closer and closer to that center line where we have basically zero reactance. So right here. Now, what happens if we have, say, too much capacitive reactance? Well, we'd be on the lower half of the Smith chart, as you can see there. Okay, so now, instead of rotating it counterclockwise, we've got to rotate it clockwise, and we can do that by adding some inductance. So let me just reposition the jumper. And you can see that we've rotated, there we are, you can see that we've rotated clockwise and moved toward the center line by increasing the inductance. So that's the interaction between the capacitor and the inductor, and that's how we can use one to cancel out the other. So now we're going to go back to our original problem here, where we had a source resistance or source impedance of 50 ohms. Okay, that's the generator or the NanoVNA. And then we've got a load resistance of 25 ohms. So I changed my load, as you can see here. Let's take a look on the Smith chart. Okay, and remember this was the constant resistance circle for 50 ohms. Okay, and this is the constant resistance circle for 25 ohms. This one's 75 ohms. So now you can see we're here. Okay, and we're going to go ahead and set up the L network and see if we can get a match between the source impedance of 50 ohms and a load impedance of 25 ohms. So the impedance transformation will be accomplished by the L network. Okay, now I've pre-adjusted the L network just to try to get it as close as possible and save some recording time. But I'll demonstrate what happens when I change the values. So here's our 25 ohm load that we just looked at. Here's our variable capacitor. So you can see I'm on this coil here, fifth coil. Okay, and then here is our variable capacitor. Okay, and it's set up series inductor, shunt capacitor. So now let's go to the Smith chart here. And basically you can see that we're basically at 50 ohms. Okay, if I read the data directly off the table here, we're at 50.8 ohms. I could adjust it closer than that. And so that's the real part. Remember, this is a complex impedance, so you see the imaginary part minus J is 3 ohms of capacitive reactance. Okay, so very, very close to 50 ohms. I could get it exact if I really play with it. But let's take a look now and see what happens when we change the amount of capacitive reactance. And we can see if we reduce the capacitive reactance, it becomes more inductive, right? And if we increase the capacitive reactance, it's going to become more capacitive. Okay, and if we adjust the capacitor slowly, we can get this back to the center line. That looks pretty good. Okay, now if we change the inductive reactance, okay, we're also going to see the center line move, okay? And we're now moving below the center line, okay, or we can move above. Let's just let it refresh here. Above, well, not quite above, but close to the center line there. You can see we're moving away from the center. In this case, it's moving to the left, and I put it here and increase, it moves to the right. So that tells me that the range of the capacitor and inductor is a good range to try to tune the 25 ohms to 10 megahertz. Of course, if we change the frequency and we want to match it at a different frequency, then we have to change the values of L and C. So I hope this was helpful. Okay, it's just a very simple L network that's used for impedance transformation. And by adjusting the values of L and C, we can match the 50 ohm source impedance from our generator here to a 25 ohm load impedance. Okay, hope this was helpful. RF Man.